Hello students. In previous video we have studied about Bohr's model of atom and the postulates of Bohr atomic model. Now we are going to apply that Bohr theory or that Bohr model conditions to the hydrogen atom. So we are dealing with hydrogen atom, that means it consists of a nucleus with a positive charge of Ze. We have a hydrogen atom. Now hydrogen has atomic number 1. That means the nucleus has positive charge of Ze, where Z is equal to 1 in case of hydrogen atom, and there is a single electron only in the orbit. It has one electron in orbit, and charge on this electron is minus E. Since it is an electron, it is minus E, and the charge on nucleus is plus Ze, where Z is equal to 1 in case of hydrogen atom. So for hydrogen, the value of Z is equal to 1. Now the electrostatic force, which is providing the centripetal force, is given as F is equal to K. Q1 Q2 means Ze into E upon R square. If R is the radius of that orbit, we can draw a diagram also. Suppose this is the orbit in which electron is revolving around this centrally located nucleus. So this is nucleus having Ze charge, where Z is equal to 1, and an electron is here which is revolving in this orbit, have some velocity v, which is denoted by the tangent on this point. Electron has mass m, and this is the distance r. So r is the radius of that orbit, or the distance of nucleus and electron. Then the electrostatic attractive force, this electrostatic attractive force is given by F is equal to K Ze into E upon R square, or it is equal to K Z E square upon R square. Right. Now this electrostatic attractive force is responsible for providing centripetal force. This is electrostatic attractive force, and this is responsible for providing centripetal force, which implies the centripetal force is equal to the value F. So centripetal force is mv square upon r. If it is moving with velocity v, then this is mv square upon r, and it is equal to kze square upon r square. On solving this, we can get the value of radius of the orbit. R is equal to kze square upon r square, right? On solving this equation, we can find the value of mv square. It will be mv square is equal to kze square upon r, and it can be rearranged to get the value of r. So let it be equation number 1. We will need this, and the value of r that we will get from equation number 1, it will be r is equal to kze square upon mv square. This is equation number 2. So mv square is equal to kze square upon r is equation number 1, and r is equal to kze square upon mv square, that is equation number 2. This is the radius of the orbit. R is representing the radius of orbit, right, in which electron is revolving with the speed v. Now from Bohr quantization condition, we know that the angular momentum L should be equal to mvr, and according to Bohr model, it is equal to nh upon 2 pi. If we solve these two values, then again we get r is equal to nh upon 2 pi mv. This is equation number 3. Since in equation number 2 and 3 we are getting the radius in both cases, we can equate these two to get the value of speed of that revolving electron. So from 2 and 3 we have kze square upon mv square is equal to nh upon 2 pi mv, and if we solve this, we get the value of speed of electron v is equal to 2 pi kze square upon nh, right? So this is the speed of electron in that orbit. Equation number 4 represent the speed of electron in that orbit. Equation number 2 and 3 both represents the radius of that orbit. Again, if we substitute the value of v in equation number 3, we can eliminate v from equation number 3. For that we get r is equal to nh upon 2 pi m v, and at the place of v we are substituting the value of v from equation number 4, which is 2 pi k z e square upon nh, and on solving this we get the radius of the orbit r is equal to n square h square 4 pi square m k z e square. This is equation number 5. So this is the final value of r, that is the radius of orbit, and it depends on all the constants. We know all the values except n. So by putting different values of n, we can find the different values of radius for every orbit. Means if we put n is equal to 1, it will give radius for first orbit. If we put n is equal to 2, it will give radius for second orbit, and so on. So equation number 5 is representing the radius of nth orbit, in which if we put the values of n, we can get the radius of all the orbits, right? Now the radii of this allowed orbits are proportional to n square. From equation number 5 we conclude that r is proportional to n square. So if we increase this value of n, the radii will increase, also the orbit size will increase, and it will be in the ratio of 1:4:9:16 and so on. Means for first orbit n is equal to 1, it will give 1 square, that is 1. For 2 it is 4, for 3 it is 9, for 4 it is 16. That means the radii of the orbits will increase in the ratio of 1:4:9:16 and so on, where n is known as principal quantum number. Now there is a term called Bohr's radius, which we represent by r naught. Let's see the term Bohr radius, which we represent by the term r naught. Bohr radius is the radius of first orbit of hydrogen atom. Radius of first orbit for hydrogen atom. That means for Bohr radius n is 1, that means the first orbit, and it is for hydrogen atom, that means z is also equal to 1. So in that case, if n is equal to 1 and z is equal to 1, we get Bohr radius r naught is equal to h square upon 4 pi square m k e square, where all these values are known. H is equal to 6.63 into 10 to the power minus 34. 4 is a constant, pi is a constant, mass of electron is 9.11 into 10 to the power minus 31. This is in joule seconds, this is in kg, and E is 1.6 into 10 to the power minus 19 coulomb. K is 9 into 10 to the power 9. So we are going to substitute all these values, and by putting all these values in this equation, we get Bohr radius is equal to 5.29 into 10 to the power minus 11 meter, or we can write it as approximately 0.53 angstrom. So this is the value of Bohr radius, or we can say that Bohr radius is the radius of first orbit of hydrogen atom. So in hydrogen atom, the radius of first orbit is called Bohr radius, and it is equal to 0.53 angstrom. Now let's talk about the speed of electron revolving, that is v. So for the speed of electron, we have find the relation in equation number 4, that is v is equal to 2 pi k z e square upon nh, which shows that speed of electron is inversely proportional to n. Now for hydrogen atom, we are talking about hydrogen, so for hydrogen atom z is equal to 1, therefore the value v is equal to 2 pi k e square upon nh, right? 2 pi k e square upon nh. Now I'm going to multiply and divide it by the factor c. This will be equal to 2 pi k e square upon ch into c upon n, and this factor 2 pi k e square upon ch is called alpha, which is the fine structure constant. This value is known as alpha. So v is equal to alpha into cn, where alpha is equal to 2 pi k e square upon ch, and its value is, since these are all constant, so its value is approximately is equal to 1 upon 137. By substituting all these values, we can solve it and get alpha is equal to 1 upon 137, and it is known as fine structure constant. So the relation we get, the speed we get is v is equal to 1 upon 137 into c upon n. Now if we are talking about the first orbit of hydrogen, in case of hydrogen, this n will be 1 and the answer we get will be v is equal to c upon 137. So for the first orbit, the speed of electron is c upon 137, right? For first orbit we have to put n is equal to 1 and we get v is equal to c upon 137. This is the speed. Now let's move to the energy of the electron. So energy of the electron includes two kinds of energy. Since it is moving, so it has kinetic energy, and also it is a charge, that's why it has electrostatic potential energy. So we have to add these two energies to get the total energy of electron. So kinetic energy of electron is half m v square, which is equal to kz e square upon 2r. By using equation number 1, we can put the value of v square here and can find that from equation number 1 we have the value of whole mv square. We can put that, or we can substitute the value of v only, then also we can calculate this. And electrostatic potential energy is k q1 q2 upon r, which can be find out as q1 is ze, q2 is minus e because of the electron, and this is r. That means potential energy is equal to k ze square upon r in negative. So we can add these two to get the total energy of electrons. So total energy of electron in nth orbit, we are talking about general orbit. So total energy of electron in nth orbit is equal to kz e square upon 2r minus kz e square upon r. And if we solve this, we get En is equal to minus kz e square upon r 2r, where we can put the value of r that we have already find. So r is the radius of nth orbit and we can substitute this value. So by putting the value of r in this equation, we get minus kz e square upon 2, and by putting the value of r, it will be 4 pi square m k z e square upon n square h square, right? 4 pi square m k z e square upon n square h square. And on solving it, we get the energy is equal to minus 2 pi square m k square z square e4 upon n square h square. So this is the energy of electron, total energy of electron in nth orbit, which is a combination of both kinetic and potential energy. Now the negative value of total energy indicates that electron is bound to the nucleus, means it is, this negative sign is representing the attraction between nucleus and the electron, or it is showing that electron is bound to the nucleus because of the electrostatic attraction. So negative sign here represent electrostatic attraction between the positively charged nucleus and negatively charged electron, and it also shows that some work is required to be done to pull it away from the nucleus. Means if we want to pull that electron away from the nucleus, we have to do some work against that attraction. That's what this negative sign is showing. So that's all for the energy, speed and radius of the electron of that orbit moving in hydrogen atom. This is the first part of the video. In second part of this video, we will be studying about the spectral series and spectral lines or energy level diagram that we get in case of hydrogen atom. For that, stay tuned and keep studying. Thank you.